Good morning everyone. My name is Radhika. I am a student of BSc Chemistry on my second year. Today I am going to read a chapter Surface Chemistry of class 12th. So let us start. Surface chemistry deals with the phenomena that occur at the surface or interfaces. The interface or surface is represented by separating the bulk phase by a hyphen or a slash. For example, the interface between a solid and a gas may be represented by a solid gas or solid hyphen gas. Due to the complete miscibility, there is no interface between the gases. The bulk phases that we come across in a surface chemistry may be pure compounds or solutions. Interface is normally few molecules thick, but its area dependent on the size of bulk phases. Many important phenomena noticeable amongst these being corrosion, electrolysis, heterogeneous catalysis, dissolution, and crystallization occur at the interfaces. The subject of surface chemistry find many application in industry, analytical work, and daily life situation. To accomplish surface studies meticulously, it becomes imperative to have a really clean surface. Under very high vacuum of the order 10 raised to power minus 8 to 10 raised to power minus 9 Pascal, it is now possible to obtain ultra clean surface of the metal. Solid metal with such clean surface need to be stored in a vacuum, otherwise these will be covered by molecule of the major components of air, namely dioxygen and dinitrogen. In this unit, you will be studying some important feature of some chemistry such as absorption, catalyst, and colloids, including emulsion and gels. Adsorption. There are several examples which reveal that surface of a solid has the tendency to attract and retain the molecule of a phase with which it comes into contact. These molecules remain only at the surface and do not differ into the bulk. The accumulation of molecular species at the surface rather than in a bulk of a solid or liquid is termed as adsorption. The molecule species or a substance which concentrate or accumulate at the surface is termed adsorbate, and the material on surface of which the absorption takes place is called absorbent. Adsorption is essentially a surface phenomena, solid particularly in finely divided state have a large surface area and therefore charcoal, silica gel, alumina gel, clay colloids, metals in finely divided state. Example act as a good adsorbent. Advantages in action. Adsorption in action. If a gas like O2, H2CO, Cl2, NH3 or SO2 is taken in a closed vessel containing powdered charcoal, it is observed that the pressure of a gas in an enclosed vessel decreases. The gas molecule concentrate at the surface of charcoal. Gases are absorbed at the surface. Second, in a solution of an organic dye, say methylene blue, when animal charcoal is added and the solution is well shaken, it is observed that the filtrate turn colorless. The molecule of a dye thus accumulate on the surface of charcoal are, that is, unabsorbed. Aqueous solution of a raw sugar, when passed over beds of animal charcoal, become colorless as the coloring substances are adsorbed by the charcoal. The air becomes dry in presence of silica gel because the water molecule get absorbed on the surface of the gel. It is clear from the above examples that solid surface can hold the gas or liquid by virtue of adsorption. The process of removing an adsorbed substance from the surface on which it absorbs is called desorption. Distinction between adsorption and absorption. In adsorption, the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the adsorbent. While in adsorption, the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, the molecule the surface retain the color of ink due to adsorption of colored molecule, while the solvent of ink goes deeper into the stick due to absorption. On breaking the chalk stick, it is found to be white from inside. A distinction can be made between absorption and adsorption by taking water vapor. Water vapor are absorbed by anhydrous calcium chloride but absorbed by silica gel. In other words, in absorption, the concentration of the adsorbate increases only at the surface of adsorbent, while in absorption, the concentration is uniformly throughout the bulk of the solid. Both adsorption and absorption can take place simultaneously. Also, the term sorption is used to describe both the processes. Mechanism of adsorption. Adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particle inside the bulk. Inside the absorbent, all the forces acting between the particles are mutually balanced, but on the surface, the particles are not surrounded by atoms or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particle on its surface. The extent of the adsorption increases with the increase of surface area per unit mass of the adsorbent at a given temperature and pressure. Another important factor featuring adsorption is the heat of adsorption. During absorption, there is always a decrease in residual force of the surface, that is, there is decrease in a surface energy which appear as a heat. Adsorption there is invariably an exothermic process. In other words, delta H of absorption is always negative. When a gas is absorbed, the freedom of movement of molecules become restricted. These amount to decrease in the entropy of gas after adsorption, that is delta S is negative. Adsorption is thus accompanied by decreases in enthalpy as well as decreases in entropy of the system. For a process to be spontaneous, the thermodynamic requirement is that at a constant temperature and pressure, delta G must be negative. That is, there is a decrease in Gibbs free. On the basis of equation, delta G is equals to delta H minus T delta S. Delta G can be negative if delta S has a significantly high negative value, as minus delta Ts is positive. Thus, in an adsorption process which is spontaneous, a combination of these two factors make delta G negative. As the adsorption proceeds, delta H becomes less and less negative. Ultimately, delta H becomes equal to T delta S and delta G becomes 0. At this state, equilibrium is attained. Types of adsorption. There are mainly two types of adsorption of gases on solid. If accumulation of gases on the surface of solid occur on account of weak van der Waals forces, the adsorption is termed as a physical adsorption or physiosorption. When the gas molecule or atom are held to the solid surfaces by chemical bond, The adsorption is termed chemical adsorption or chemosorption. The chemical bond may be covalent or ionic in nature. Chemosorption involves a high energy of activation is and is therefore often referred as activated adsorption. Sometimes these two processes occur simultaneously and it is not easy to ascertain the type of adsorption. A physical adsorption at a low temperature may processes into chemosorption as a temperature is increased. For example, dihydrogen is first absorbed on nickel by van der Waals forces. Molecule of hydrogen then dissociate to form hydrogen atoms which are held on a surface by chemosorption. Some of the important characteristics of both types of adsorption are described below. Characteristic of adsorption: lack of specificity. A given surface of an adsorbent does not show any preference for a particular gas as the van der Waals forces are universal. Nature of the adsorbate: the amount of gas absorbed by a solid dependent on the nature of the gas. In general, easily liquefiable gases, that is with a higher critical temperature, are readily absorbed as a van der Waals forces are stronger near the critical temperature. Thus, 1 gram of activated charcoal absorbs more sulfur dioxide critical temperature 630 Kelvin than methane critical temperature 190 Kelvin, which is still more than 4.5 ml of dihydrogen critical temperature 33 Kelvin. Second, reversible nature. Physical adsorption of gas by solid is generally reversible. Thus, solid plus gas, solid hyphen gas plus heat. More of gas is absorbed when pressure is increased as the volume of gas decreased. Le Chatelier's principle, and the gas can be removed by decreasing pressure. Since the adsorption process is exothermic, the physical adsorption occurs readily at the low temperature and decreases with increasing temperature. Le Chatelier's principle. Surface area of adsorbent. The extent of adsorption increases with the increase of surface area of adsorbent, and thus finally divided metal and porous substances having large surface area are good absorbent. Enthalpy of adsorption. No doubt, physical adsorption is an exothermic process, but its enthalpy of adsorption is quite low, 20-40 kilojoule mole inverse. This is because of the attraction between gas molecules and solid surface is only due to weak van der Waals forces. Characteristic of chemosorption. High specificity. Chemosorption is highly specific and it will only occur if there is some possibility of a chemical bonding between absorbent and adsorbate. For example, oxygen is adsorbed on metal by virtue of oxide formation, and hydrogen is adsorbed by transition metals due to hydride formation. Irreversibility. As chemosorption involves compound formation, it is usually irreversible in nature. Chemosorption is also an exothermic process, but the process is very slow at low temperature on account of high energy of activation. Like most chemical changes, adsorption often increases with rise of temperature. Desorption of a gas adsorbed at a low temperature may change into chemosorption at a high temperature. Usually, high pressure is also favored for chemosorption. Surface area. Like physical adsorption, chemosorption also increases with the increase of surface area of the adsorbent. Enthalpy of adsorption. Enthalpy of chemosorption is a high, 82 to 40 kilojoule mole inverse, as it involves chemical bond formation. Comparison of physisorption or chemisorption. Physioption. It arises because of van der Waals forces. Chemioption. It is caused by a chemical bond formation. It is a specific in nature. It is highly specific in nature. It is reversible in reaction. It is irreversible. It depends on nature of a gas. More easily liquefiable gases are adsorbed readily. It also depends on the nature of gas. Gases which can react with adsorbent show chemisorption. Enthalpy of adsorption is low, enthalpy of adsorption is high. Low temperature is favorable for adsorption. It decreases with increases of temperature. High temperature is favorable for adsorption. It increases with the increase of temperature. No applicable activation energy is needed. High activation energy is sometimes needed. It depends on the surface area. It increases with the increase of surface area. It also depends on the surface area. It too increases with an increase in surface area. It results into multi-molecular layer on adsorbent surface under high pressure. It results into unimolecular layer. Adsorption isotherm. The variation in amount of gas absorbed by a adsorbent with the pressure at a constant temperature can be expressed by means of a curve termed as adsorption isotherm. Freundlich adsorption isotherm. Freundlich in 1909 gave an empirical relationship between the quantity of gas absorbed by unit mass of solid adsorbent and the pressure at a particular temperature. The relationship can be expressed by the following equation, where x is the mass of gas absorbed on a mass m of the adsorbent at a pressure P. K and N are constant which depend on the nature of the adsorbent and the gas at the particular temperature. The relationship is generally represented in a form of curve where mass of a gas adsorbed per gram of the adsorbent is plotted against pressure. These curves indicate that at a fixed pressure there is a decrease in a physical adsorption with increase in temperature. These curves always seem to approach situation at a high pressure. Taking logarithm of equation 5.1, the validity of Freundlich isotherm can be verified by plotting log x by m on y-axis ordinate and log p on x-axis abscissa. If it comes to be a straight line, the Freundlich isotherm is valid, otherwise not. The slope of the straight line gives the value of 1 by n. The intercept of y-axis gives the value of log k. Freundlich isotherm explains the behavior of adsorption in an appropriate manner. The factor 1 by n can have values between 0 and 1, probable range between 0.1 to 0.5. Thus equation 5.2 hold good over the limited range of pressure. When 1 by n equal to 0, x by m constant and the absorption is independent of pressure. When n by n equal 1, x by m k p, that is x by m directly proportional to p, the adsorption varies directly with pressure. Both the conditions are supported by experimental results. The experimental isotherm also seem to approach saturation at high pressure. This cannot be explained by Freundlich isotherm, thus it fails as a high pressure. Adsorption from solution phases. Solid can adsorb solutes from solution also. When a solution of acetic acid is in water is shaken with a charcoal, a part of acid is absorbed by a charcoal and the concentration of acid decreases in the solution. Similarly, the litmus solution, when shaken with a charcoal, becomes colorless. The precipitate of MgOH twice attains blue color when precipitated in presence of magnesium reagent. The color is due to the adsorption of magnesium. The following observation may have been made in case of adsorption from solution phase. The extent of adsorption decreases with the increase in temperature. The extent of adsorption increases with the increase of surface area of the adsorbent. The extent of adsorption depends on the concentration of a solute in solution. The extent of the adsorption depends on the nature of the adsorbent and the adsorbate. The precise mechanism of adsorption from solution is not known. Fredolic equation approximately describes the behavior of adsorption from solution with the difference that instead of pressure, concentration of the solution is taken into account. C is a equilibrium concentration, that is when adsorption is complete. On taking logarithm of the above equation, we have plotting log x by m against log c is a straight line is obtained which shows the validity of Fredolic isotherm. This can be tested experimentally by taking solution of different concentration of acetic acid. Equal volume of solution are added to the equal volume of charcoal in different flask. The final concentration is determined in each flask after adsorption. The difference in the initial and final concentration give the value of x. Using the above equation, the validity of Fredolic isotherm can be established. Application of adsorption. The phenomena of adsorption finds a number of applications. Important one are listed here. Production of high vacuum. The remaining traces of air can be absorbed by charcoal from a vessel evacuated by a vacuum pump to give a very high vacuum. Gas mask. Gas mask is a device which consists of activated charcoal or mixture of absorbent. Is usually used for breathing in a coal mines to absorb poisonous gas. Control of humidity. Silica and aluminum gets used as an adsorbent for removing moisture and controlling humidity. Removal of coloring material from solutions. Animal charcoal remove color of solution by adsorbing colored impurities. Heterogeneous catalyst. Adsorption of reactant on a solid surface of the catalyst increases the rate of reaction. There are many gaseous reactions of industrial importance involving solid catalyst. Manufacturing of ammonia using iron as a catalyst, manufacture of ester by a contact process, and use of finely divided nickel in a hydrogenation of oil are an excellent example of heterogeneous catalysts. Separation of inert gases. Due to the difference in degree of adsorption of gases by charcoal, a mixture of normal gas can be separated by adsorption in a coconut charcoal at a different temperature. In curing disease, a number of drugs are used to kill germs by getting adsorbed on them. Froth flotation process. A low-grade sulfide ore is concentrated by separating it from silica and other earthy matter. By this method, using pine oil and frothing agent. Adsorption indicator. Surface of a certain precipitates such as silver halide have the property of absorbing some dyes like eosin, fluorescein, etc., and thereby producing a characteristic color at the end point. Chromatographic analysis. Chromatographic analysis based on the phenomena of adsorption find a number of applications in analytical and industrial field. Catalysis. Potassium chlorate, when heated, strongly decomposes, slowly giving dioxygen. The decomposition occurs in a temperature range of 653 to 873 Kelvin. However, when a little of manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, 473 to 633 Kelvin, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition in a similar manner. The rate of a number of chemical reaction can be altered by a more presence of foreign substances. The systematic study of effect of the various foreign substances in the rate of chemical reaction was first made by Berzelius in 1835. He suggests term catalyst for such substances. Substances which under the rate of chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts. The phenomena is known as catalysis. You have already studied about catalyst and functioning in section 4.5, promoter and poisons. Promoter are substances that enhance the activity of a catalyst, while poison decreases the activity of catalyst. For example, in a Haber's process for manufacturing of ammonia, molybdenum acts as a promoter for iron, which is used in the catalyst. Catalyst can be broadly divided into two groups: homogeneous catalyst and heterogeneous catalyst. Homogeneous catalyst. When the reactant and the catalyst are in the same phase, that is liquid or gas, the process is said to be homogeneous catalyst. The following are some of the examples of homogeneous catalyst: oxidation of sulfur dioxide into sulfur trioxide with dioxygen in presence of oxide of nitrogen as the catalyst in the Lead-Chauver process. The reactant sulfur dioxide and oxygen and the catalyst nitric oxide are all in the same phase. Second, hydrolysis of methyl acetate is characterized by H positive ions furnished by hydrochloric acid. Both the reactant and the catalyst are in the same phase. Hydrolysis of sugar is catalyzed by H positive ion furnished by sulfuric acid. Both the reactant and the catalyst are in the same phase. Heterogeneous catalyst. The catalytic process in which the reactant and the catalyst are in a different phase is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysts are oxidation of sulfur dioxide into sulfur trioxide in the presence of platinum. The reactant is in gaseous state while the catalyst is in a solid state. Combination between dinitrogen and dihydrogen to form ammonia in presence of finely divided iron in Haber's process. The reactant are in a gaseous state while the catalyst in a solid state. Oxidation of ammonia into nitric oxide in presence of platinum goes in Ostwald process. The reactant are in a gaseous state while the catalyst is in a solid state. Hydrogenation of vegetable oil in presence of finely divided nickel as a catalyst. One of the reactant is in liquid state and the other in gaseous state while the catalyst is a solid state. Adsorption theory of heterogeneous catalyst. This theory explains the mechanism of heterogeneous catalyst. The old theory known as adsorption theory of catalyst was that the reactant in a gaseous state or a solution are adsorbed on the surface of a solid catalyst. The increase in concentration of the reactant on the surface increases the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of the reaction. The catalytic action can be explained in terms of intermediate compound formation. The theory which we have already studied in section 4.5.1. The modern adsorption theory is the combination of intermediate compound formation and the old adsorption theory. The catalytic activity is localized on the surface of catalyst. The mechanism involves 5 steps. Diffusion of reactant to the surface of catalyst, adsorption of the reactant molecule on the surface of catalyst, occurrence of chemical reaction on the catalyst surface through formation of intermediate, desorption of reaction products from the catalyst surface and thereby making the surface available again for more reaction to occur. Diffusion of reaction product may away from the catalyst surface. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with the subject surfaces, its molecules are held up there due to the Lewis chemical combination. If different molecules are adsorbed side by side, they must react with each other, resulting in the formation of new molecule. Thus, formed molecule may evaporate, leaving the surface of a fresh reactant molecule. This theory explains why the catalyst remain unchanged in mass and chemical composition at the end of reaction and is effective even in a small quantities. It, however, does not explain the action of the catalytic promoters and catalytic poisons. In important feature of solid catalyst. Activity. The activity of a catalyst depends upon the strength of a absorption to a large extent. The reactants must be absorbed reasonably strongly on the catalyst to become active. However, they must not get absorbed so strongly so that they are immobilized and the other reactant are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals with the maximum activity being shown by group 7 to 9 elements on the periodic table. Selectivity. The selectivity of a catalyst is its ability to direct the reaction to yield a particular product. For example, starting with H2 and CO and using different catalysts, we get different products. Thus, it can be inferred that the action of catalyst is highly selective in nature, that is, a given substance can act as a catalyst only in a particular reaction and not follow the reaction. It means that the substance which acts as a catalyst in one reaction may fail to catalyze another reaction. Shape selective catalyst by zeolites. Thus, catalytic reaction that depend upon the pore structure of the catalyst and the size of the reaction and product molecule is called shape selective catalyst. Zeolites are a good shape selective catalyst because of their honeycomb-like structure. They are microporous aluminum silicates with a three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atom, giving aluminum or silicon framework. The reaction taking place in zeolite depends upon the size and the shape of reactant and the product molecule as well as upon as the pores and in the cavity of the zeolites. They are found in nature as well as synthesized for a catalytic selectivity. Zeolites are being very widely used as catalysts in a petrochemical industry for cracking of hydrogen and isomerization. An important zeolite catalyst used in a petroleum industry is ZSM5. It converts alcohol directly into gasoline petrol by degrading them to give a mixture of a hydrocarbon. Enzyme catalyst. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of a high molecular mass and form colloidal solution in the water. They are very effective catalyst. Catalyzes numerous reactions, especially those connected with the natural processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are thus termed as a biochemical catalyst and as phenomena is known as a biochemical catalyst. Many enzymes have been obtained in the crystal living cells. However, the first enzyme was synthesized in laboratory in 1969. The following are some of the examples. Conversion of cane sugar. The invertase enzyme converts cane sugar into glucose and fructose. Conversion of glucose into ethyl alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. Conversion of starch into maltose. The disaster enzyme converts starch into maltose. Conversion of maltose into glass. The maltase enzyme converts maltase into glucose. Decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes the decomposition. In stomach, the pepsin enzyme converts protein into peptides, while in intestine, the pancreatic toxin converts protein into amino acid by hydrolysis. Conversion of milk into curd. It is an enzymatic reaction both occurred via lactobacilli, an enzyme present in curd. Some enzymatic reactions. Characteristic of enzyme catalyst. Enzyme catalyst is unique in efficiency and a high degree of specificity. The following characteristics are exhibited by enzyme catalyst. Most highly efficient. One molecule of an enzyme may be transferred 1,000,000 molecules of the reactant per molecule. High specific nature. Each enzyme is specific for a given reaction One catalyst cannot analyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrogenation of one amide. Highly active under optimum temperature, the rate of enzyme reaction becomes maximum at the definite temperature called the optimum temperature. On either side of the optimum temperature, the energy activity decreases. The optimum temperature range for a enzymatic activity is 298 to 310 Kelvin. Human body temperature being 310 Kelvin is suited for an enzyme catalyzed reaction.